works for company IST in Switzerland.
Exactly.
Are you already able to speak some Schweizerdeutsch? Or
I think I'm not allowed to say that.
Okay, so we stay with English. So the topic will be about ceramic sensors for temperature, flow, and humidity monitoring. Laura is an expert for flow sensors, so I think this talk will be very interesting.
Exactly.
Have fun.
All right. Thanks a lot for the nice introduction. You already said it yourself. So the main goal of today's talk is going to be to answer the question, what can we do to assure that a sensor will perform in the field even under rough conditions? So by the end of this talk, I will have introduced different sensing techniques and different challenges that we had over the years with our customers, and hopefully you will be able to get an answer for the problem that you're currently dealing with. So as he already said, I'm Sobral Rey. I'm an R&D engineer for Flow. I work at IST. It's a company that has its headquarters based in Switzerland. You can see it here on the big picture. And we are overworld. So like we have many different locations. All good with the song? Okay. So for dealing with today's topic, we thought that we would separate it in these 4 different blocks. So in the first one, we will introduce what is the ceramic technology and how we have optimized different solutions for extreme conditions. And then we will focus on the 3 different sensing principles. That will be temperature, flow, and humidity. And then at the end, we will do like a small wrap-up, and we will come to the conclusions. So starting from the beginning, and since I am the first speaker of the season, I thought that we come all together into the same page. So condition monitoring purpose is to predict failures before they occur. Now, what causes these failures? So there might be many reasons. First, for instance, might be mechanical. We have a system with high vibrations, high pressure salts, or high pressure in general. It might be due to extreme temperatures, either because it's low temperature or very high temperature, or because we are talking about temperature cycles, or because the environment itself is not clean or it's very challenging. So we are dealing with dust, with grease, or with harsh chemicals. Now the trick is that the sensor itself also needs to survive these rough conditions, right? And the question is how we do it, or how can we develop a sensor that faces these tough conditions and that survives it. So to answer that question first, we would like to introduce how is the sensor, or how are our chips produced. So we start by a ceramic substrate. On top of the ceramic substrate, we spatter a thin layer of platinum. And then on this thin layer of platinum, we can pattern different structures by lithography, resist spin coating, and developing. This we can repeat several times to create different layers from different materials. This is what we call thin film. We also have the possibility of doing thick film, which would be, for instance, for having at the ends a glass layer that would protect the final meander. What is special about our process technique is that we deliberately make these meanders with a lower resistance than it should have at the end. And we can then trim this structure to a very precise value. So then, this is how the basic structure would look for most of our sensors. And this is already part of the answer of why this is so robust. So we have at the base a ceramic base. Then on top of it, it comes a platinum structure, and on top of it is a glass. These are very few materials, very few wet materials. And they are all very robust by definition. Last step on the sensor producing would be to weld some wires on it and to cover these wires with a special paste that secures these wires into it. And now that's just to give you a feeling of how big or how small these sensors can be. So it can go from the ranges of a few centimeters down to sizes that go below millimeters. As a small parenthesis from our talk, we would like to shortly introduce what are all the different things that we do. So we do all sort of
all sort of measurement principles, going from heaters to conductivity to infrared. And if any of this gets your eye, we would love to invite you to our booth and to discuss this with you. But for today's session, we will focus on the ceramic sensors, and in particular for the temperature, flow, and humidity. So moving forward into that and starting by temperatures, over the years, we had many projects that were dealing with very high temperatures. And the natural question for us was if we could develop similar sensors that could be used for extremely low temperatures. Here the challenge, and this is what you can see in the plot here, is that the sensitivity of the platinum sensors decreases a lot by low temperatures. Here you see how much the resistance changes with the temperature versus temperature. And this is what one sees here. However, what we also measured is that when we individually calibrate the sensors, the accuracy that they deliver is still quite good. So what you have in the upper plot are individually calibrated sensors. And what we are plotting here is the deviation of the temperature that they measure versus the temperature. So especially for temperatures above 20 Kelvin, one sees that this accuracy remains excellent and can be used quite precisely. What is now part of the core knowledge is to extend this calibration that we did for just a few sensors to the whole batch. So like to control actually the conditions and the impurities that we have in the platinum to actually be able to use this for the whole batch. So this is what we did in the second plot. Here is like the so-called batch sensors, and this is the accuracy that they deliver. So as you can see, also above 20 millikelvin is extremely good. So this showed us that we can use platinum sensors down to extremely low temperatures, and they can be done in two available precisions. Either we deliver an individual polynomial for each of the sensors, and then the precision would be plus minus 200 millikelvin, or we have one polynomial for the whole batch, and this would be 3 Kelvin. The advantages of this is that this is a very cost-efficient solution, and that one can use the same sensor for a very wide temperature range. Now, another question that we also normally have is that the sensor may not come in contact with the media or vice versa. So for that, we have developed this technique for packing the sensor in a polyimide layer. So we start with the temperature sensor element, and we do like a sandwich where we have polymers left and right. And to stick these two together, we put a polymer in the middle. The key here is to make this in a way that it's as small as possible and as thin as possible so that we don't have a lot of extra material that comes in contact with the medium. This is how the sensor looks like. And what is special then is that this packaging protects these wires and these soldering contacts, as well as the sensor laterals. We have tested this with the possibility of sticking it directly. In this case, the temperature can go up to 150 degrees, and without the sticker, it can go up to 200 degrees. So the first results have shown that the measurements of the temperatures are extremely precise. So basically, we measure pretty much as if it wasn't without this extra layer of material, and there is no water absorption. And further tests that we are doing are like vibration tests, chemical inert tests, and extensive IP tests, and these are also so far quite good. So this was about temperature, and the question now is how can we extend this ceramic sensing to flow sensing? So for that, I would like to start by explaining what are the two measurement principles that we use for flow sensing. The first is calorimetric principle. So for that, we have two temperature sensors, left and right, and a heater in the middle. We apply a power in the heater, and then when there is no flow, we will have a cloud that is formed on top of the heater. While applying some flow, this cloud would move from one of the heaters. So while having a constant power, we would measure a different delta T, and this is what we can correlate with the flow to measure flow. The anemometric principle is very similar. So we will have, in this case, just a temperature sensor and a heater. And in this case, what we want to do is that the delta T is constant. When we have a flow, this cloud that we had on top of the heater will move. And in order to keep this delta T constant, we will have to apply more power. So in this case, while keeping delta T constant, we will have a correlation between the power and the flow that we want to measure. So based on these two measurement principles, we have developed these two chips. One is the FS2, it's based on the calorimetric principle. From the principle itself, it can detect the flow direction, and it also has an extra temperature monitoring. And the FS7 can be smaller because we don't need the extra temperature sensor, and it has therefore also faster response time. This is how the raw output looks like, in particular for the FS7. And what we have proven over the years is that this output depends on many variables. It depends on the geometry. So how do we exactly install the sensor inside of the channel? What is the temperature that we use while operating it and while calibrating it? And also building know-how in order to avoid turbulences around this sensor. So with all of this knowledge that we have accumulated over the years, we have developed this FS module. Here inside this channel, there is an FS sensor installed, and on top of this, there is like a PCB that will give you a direct flow output. Here down, there is a plot where we put the output of this FS module against a reference. And what you can see is that it's already quite good, so it's like all of the points are laying on the gray line. The accuracy shows that's much better because it's a value that measures what is the difference between each of these points and the gray line. And you can see that for all the flow range stays within the limits. And the repeatability, it's a measurement that gives you a feeling of how noisy the signal is. And it also remains quite low, so below 0.5% for the whole flow range. What we also tested was to do the same test at different conditions, so different rough conditions, different temperatures. The flow output is not altered. I thought we have different temperatures here for all the flow range. And we also did a similar test for different pressures. And also here there is like no change or not worse accuracy response. So we have, all in all, a very robust solution that is cost optimized. And what is also special is that it's customizable. So we can customize it for different gases, for different flow ranges, and for different diameters from the connector. Another question, or that is also important regarding ceramic sensors, is that the fact that they are robust enables to make a robust packaging out of them. And in that sense, we wanted to present here two examples. One is this glass-spotted FS sensor. So what we have here is a ceramic sensor. This rounded is like a stainless steel housing, and the only material that we use to stick the stainless steel to the ceramic sensor is glass. This gives a quite robust solution or elegant solution because this allows to directly install it in the final application. And what is interesting is that these are all very little and very robust materials, and we don't compromise the sensitivity because nothing comes on top of the sensor. And what is more important is that the resistance of the sensor before this housing process and after this housing process is unaltered, meaning that it's unaffected by this. Another possibility, when nothing should contact the sensor or vice versa, the media should not be contacted by anything, is to solder the sensor on top of stainless steel surfaces. And this is what we have here as an example for the real proof. So this is, here this is a temperature sensor soldered on the bottom of this tube. And here is a flow sensor because we have a temperature sensor and a heater. The key here is to do this salting point as small as possible or as thin as possible to not compromise the sensitivity. And what is very good about this solution is that the media just is in contact with the stainless steel, which means like a very robust and dirt-resistant solution. And what we are showing here is that I thought we have this extra material. So from stainless steel and soldering, the response time is not affected, so it's still quite fast. And the sensors still have extremely high sensitivity because it's possible to detect very small flows and to differentiate between them. Just as a small hint, also this OOL solution we offer as an OOL module that has a direct flow output. And now coming into a little bit more focus on the flow condition monitoring. So we have two solutions that are pretty adapted to this topic. One is for gas or for flow sensing, so from 0 to a certain amount of flow. This is the flow switch. The detection is bus based on two ceramic SMDs, and it has like an integrated electronics. And the sensitivity is quite good because the response of the signal is the best at lower flows. And we also have a solution that is for liquids. So it's measuring bubbles or like gas inside the liquid. The working principle here is because we have different thermal conductivities between these two elements. And what you see here is in orange what the heater behavior would be when several bubbles are coming in, bubbles that are below 1 millimeter. And the blue signal is the signal that the bubble detector gives. So it's like an on and off signal. The response time, as you can see, is also quite fast because here we have a scale that goes to below a second. And as you can see, it takes less than 50 milliseconds to detect the bubbles. That would be for flow. For humidity, the question is how we can enable or make this technology, ceramic technology, work for humidity. So we base that on a capacitance measurement. We have two plates, basically, and in the middle there is a polymer, and this polymer has the ability to absorb or dissolve water. Now, depending on the amount of water that it has absorbed, it will have a different relative permittivity, and this would give a different capacitance. So here, what we can correlate is the capacitance to the amount of humidity. Here, the lower picture is how it looks like in a chip form. So we have a bottom electrode and a top electrode, and on the middle you have this polymer that is able to absorb and dissolve water. So the question here comes down to the polymer itself. And over the years, we have developed different polymers that are tackled for different solutions or that are tackled for different applications. So starting here, the P14 is the all-rounder, so it can work for many things. Here we have tested it after a stress, which is like different pressure cycles. So we have different samples into a chamber where we put pressures from 0 to 14, and then we test the sensor to see if it's still delivering. And as you can see, the deviation on the relative humidity is extremely low for all humidities. And another one that we have developed for extremely low humidities is the CAP5. So here you have the measurements of 6 modules over different frost points. And as you can see, the accuracy also remains quite good despite going to quite low. For humidity, as for the previous cases, we can offer this in the form of an element, in the form of a module. So that means with an integrated electronics and calibrated, or as a probe that it's already ready to be installed in the final application. And when we are talking about tough conditions or rough conditions, the MK33 is the one polymer that we have developed that has shown over the years that is quite robust. So the first measurements or results that I'm going to be presenting here are like measurements after a temperature cycle between minus 40 and 85 degrees, and then humidity measurements at room temperature. So while others' accuracy comes outside of the tolerance range, the MK33 stays on range and for many more samples as for the others. And the final test that we did with this type of sensors was like very long time test in oil, so like in a relative corrosive media. What you see here is the humidity response against time, which is over a year for 2 different types of oils. And as you can see, well, first, it's remarkable that it's working during this long period of time. And second, it's quite reliable and quite constant. I'm about to be finished. This change is basically due to the change of temperature or to the oil itself that can react better or worse to humidity. So exactly, this would be a bit the conclusion of this slide. The MK33 is the most robust polymer that we have developed for rough conditions. So with this, we can move to the conclusions. So the first thing that we see is that ceramic sensors are by definition robust. That's because there are very little wet materials, almost two, so glass and ceramic, and they are very robust by definition. Second is that they deliver accuracy despite extreme conditions. We saw that for temperature, where the temperature measurement can still be very accurate, even though there are even thought at very low temperatures, so 20 Kelvin. We saw that for flow, for the FS module, where the accuracy was still very good, also despite different temperatures or different pressures. And we just saw now for the MK33, which was able to measure over extremely long period of times and was also able to deliver good accuracy after a temperature stress test. This robust technology enables then robust packaging. We saw that in the case of temperature from this polyimide laminated solution, but also for temperature and flow, because it's possible to solder these sensors on top of a stainless steel surface, or because it's possible to make a probe out of it. And then last but not least, okay, this is robust packaging can also apply to the glass sensing. These are all multidisciplinary solutions, meaning that they don't tackle just one problem. They solve different problems at a time. So for instance, this glass sensor is pressure resistant, so it can be used up to extremely high pressures, but it's also chemical resistant. And also in the sense that we can use different sensing elements to make multidisciplinary parameters modules. So with that, I will be open for questions, either now or at our booth. We will be more than happy to have you there. And I would like to say thank you for your time.
Well, thank you, Laura. Perfect in time. And so, are there any questions? Don't be shy. We have a little time left, so there's time for questions. Yes.
Thank you for the nice presentation. I have a question on the MK33.
Yes.
Can it withstand a saturation with water? So do these sensors come back to normal measurements if they were saturated with water for quite some time?
I think so, yes. I mean, well, I'm here the flow expert, first to say, so I think it would be great if you could come later to discuss this with Darren, the engineer, but I think so because these measurements here are done in a closed glass. You're not seeing my screen anymore. Okay, so basically the measurements that I showed, the two plots, are done in a glass that was in condensation. So these temperature cycles were done in a glass in condensation, and then afterwards we measure them at different humidity levels. So I think so.
So we have another expert here.
You can put the sensor element in water or in coffee, and after evaporating of water from the surface, the sensors will operate normally, the same as before.
Okay, thank you. So I think the guys will be happy to help you. The booth is 308 IST, and you will be welcome, I'm sure, to see. So, any other questions? No, not for the moment. For all of you, if there are questions and if you want to have more information, the booth is 308 and the company is IST, which is just in front at the entrance, so you can't miss it. So thank you, Laura. And I see our next speaker is already nearly ready.